Running number 4 copper around the footing before the concrete is poured can be an effective grounding electrode. Brown rods are typically used as grounding electrodes. In this case, the fieldstone foundation and basement floor can make it challenging to install them effectively. Concrete encased copper conductors, such as number 4 copper around the footing, can also be used as grounding electrodes. The concrete provides a conductive path to the surrounding soil, which acts as the grounding medium. Placing the copper around the footing ensures that it is in close contact with the concrete and the soil beneath it, maximizing the grounding potential. The number 4 copper should be bonded to the electrical panel and any other grounding points in the system. This creates a low resistance pathway for fault currents to flow into the ground. The effectiveness of any grounding electrode depends on the conductivity of the surrounding soil. If the soil is dry or non-conductive, the grounding may not be sufficient. Copper is a relatively corrosion-resistant material, but it can still be affected by moisture and chemicals in the soil. Consider using a corrosion-resistant compound or coating on the copper to prolong its life. Check with local building codes to ensure that this method of grounding meets the required standards. In summary, running number 4 copper around the footing before the concrete is poured can be an effective grounding electrode. It provides a conductive path to the soil, which serves as the grounding medium. Ensure proper bonding to the electrical panel and consider the soil conditions and corrosion protection for optimal performance. Several factors contribute to the effectiveness of this method. Firstly, the National Electrical Code, or NEC, recognizes concrete encased electrodes as a valid grounding method. These are often referred to as UFA grounds. Secondly, the size of the copper conductor is important. Number 4 copper is a common and acceptable size for grounding electrodes, but local codes might specify a different size, so it's crucial to verify. Thirdly, the depth and coverage of the concrete are important. The more contact the concrete has with the earth, the better the grounding. Fourthly, proper bonding to the main electrical panel and other grounding points within the house is essential for creating a low impedance path for fault currents. Fifthly, the soil type affects grounding effectiveness. Sandy or rocky soil is less conductive than clay soil, so the type of soil around the foundation can influence how well the grounding system works. Sixthly, consider using a corrosion inhibitor on the copper conductor. This is especially important in soils with high acidity or alkalinity, which can accelerate corrosion. Seventhly, document the grounding system. Keep records of the grounding system installation, including the location of the copper conductor, the type of soil, and any corrosion protection measures taken. This will be helpful for future maintenance and inspections. Eighthly, consult a qualified electrician. Upgrading an electrical service and installing a grounding system are complex tasks that should be performed by a qualified electrician. They can ensure that the work is done safely and in accordance with local codes. Ninthly, consider supplementary grounding electrodes. Even with a concrete encased electrode, it may be necessary to install additional ground rods or other grounding electrodes to meet code requirements or improve grounding performance. Tenthly, periodic inspections. Grounding systems should be inspected periodically to ensure that they are still in good condition and functioning properly. This is especially important in older homes where the grounding system may have deteriorated over time. 11thly, consider the potential for ground faults. A ground fault is an unintentional electrical path between a live conductor and ground. Ground faults can be dangerous and can cause electrical shock or fire. A properly installed grounding system can help to protect against ground faults by providing a low impedance path for fault currents to flow back to the source. 12thly, ground fault circuit interrupters or GFCIs. GFCIs are devices that can detect ground faults and quickly interrupt the flow of electricity. GFCIs are required in many areas of the home, such as bathrooms, kitchens, and outdoor outlets. 13thly, surge protection. A surge protector is a device that protects electronic equipment from voltage spikes. Voltage spikes can be caused by lightning strikes, power outages, or other electrical disturbances. A properly installed grounding system can help to divert surge currents away from electronic equipment, protecting it from damage. 14thly, bonding of metallic water pipes. Metallic water pipes can act as grounding electrodes if they are in contact with the earth. However, it is important to bond metallic water pipes to the electrical grounding system to ensure that they are at the same electrical potential. 15thly, bonding of gas pipes. Gas pipes should not be used as grounding electrodes. However, gas pipes should be bonded to the electrical grounding system to ensure that they are at the same electrical potential. 16thly, labeling. Clearly label the grounding system components, such as the grounding electrode conductor and the grounding electrode. This will help to ensure that the system is properly maintained and that it is not accidentally disconnected. 17thly, grounding electrode conductor size. The size of the grounding electrode conductor must be sufficient to carry the available fault current. The size of the grounding electrode conductor is determined by the size of the service entrance conductors. 18thly, grounding electrode conductor material. The grounding electrode conductor can be made of copper, aluminum, or copper-clad aluminum. The grounding electrode conductor must be protected from physical damage. 19thly, grounding electrode connections. Grounding electrode connections must be made using approved connectors. Grounding electrode connections must be accessible for inspection and testing. 20thly, ground resistance testing. Ground resistance testing should be performed to verify the effectiveness of the grounding system. Ground resistance testing should be performed by a qualified electrician. 21st, National Electrical Code requirements. The National Electrical Code, or NEC, contains detailed requirements for grounding and bonding. The NEC is updated every 3 years, so it is important to stay up to date on the latest requirements. 22nd, Local Electrical Codes. Local electrical codes may have additional requirements for grounding and bonding. It is important to check with the local building department to determine the specific requirements for the area. 23rd, safety precautions. Working with electricity can be dangerous. It is important to take safety precautions to protect yourself from electrical shock. Always disconnect power before working on electrical equipment. Wear appropriate personal protective equipment, such as rubber gloves and safety glasses. 24th, qualified electrician. If unsure about how to install or maintain a grounding system, it is best to consult a qualified electrician. A qualified electrician has the knowledge and experience to perform the work safely and correctly. 25th, understanding grounding vs bonding. Grounding and bonding are two distinct but related concepts in electrical systems. Grounding refers to connecting the electrical system to the earth, providing a path for fault currents to flow back to the source. Bonding refers to connecting metallic parts of the electrical system together to create a low impedance path for fault currents. 26th, importance of low impedance. A low impedance path is essential for effective grounding and bonding. Impedance is the opposition to the flow of alternating current. A high impedance path will limit the flow of fault current, which can increase the risk of electrical shock or fire. 27th, types of grounding electrodes. There are several types of grounding electrodes that can be used, including ground rods, ground plates, and concrete encased electrodes. The type of grounding electrode that is best suited for a particular application will depend on the soil conditions, the size of the electrical system, and local code requirements. 28th, ground rod installation. Ground rods should be driven into the earth to a depth of at least 8 feet. Ground rods should be spaced at least 6 feet apart. Ground rods should be made of copper or copper-clad steel. 29th, ground plate installation. Ground plates should be buried in the earth to a depth of at least 30 inches. Ground plates should be made of copper or galvanized steel. 30th, concrete encased electrode installation. Concrete encased electrodes should be encased in at least 2 inches of concrete. Concrete encased electrodes should be located near the bottom of the foundation. 31st, testing grounding systems. Grounding systems should be tested periodically to ensure that they are functioning properly. Grounding systems can be tested using a ground resistance meter. Ground resistance meters measure the resistance between the grounding electrode and the earth. 32nd, acceptable ground resistance. The acceptable ground resistance for most electrical systems is 25 ohms or less. If the ground resistance is higher than 25 ohms, the grounding system should be inspected and repaired. 33rd, troubleshooting grounding systems. If suspect there is a problem with the grounding system, there are several things to check. Check the grounding electrode connections to make sure they are tight and corrosion-free. Check the grounding electrode conductor to make sure it is not damaged. Check the ground resistance to make sure it is within the acceptable range. 34th, maintaining grounding systems. Grounding systems should be inspected periodically to ensure that they are functioning properly. Grounding electrode connections should be cleaned and tightened as needed. Damaged grounding electrode conductors should be replaced. Ground resistance should be tested periodically. 35th, importance of proper grounding. Proper grounding is essential for electrical safety. Proper grounding can help to protect against electrical shock and fire. Proper grounding can also help to protect electronic equipment from damage. Therefore, ensuring a proper grounding system is critical.